Good evening, ladies and gentlemen, and welcome to another one of our series of lectures of the Our Changing World series of public lectures. We have tried to produce a very diverse range of topics. They're all clustered around boundaries, but we've moved through many different topics, and we've moved, I suppose, from matters of state to tonight's states of matter. It's my great privilege to introduce Chris Stock, who has come from Toronto, where he did his bachelor's and his PhD, and then worked as a postdoctoral researcher in Johns Hopkins, and started to follow some of the places in the world where you can view matter at its very craziest. He worked in ISIS and DIDCOT in this country, and the Center for Neutron Research in the USA. And we're very fortunate that he then came to Edinburgh to a position in the School of Physics and Astronomy, where he researches and teaches in the area about which he's going to tell us tonight. Chris.
I got this one. Thanks very much for the kind introduction, and thanks for coming. Hopefully, I think the mic's working okay. So, anyways, just to move on to the bulk of the talk. So there's kind of three ideas, actually, that I want to talk about today. So looking at the program, I realized I'm sort of out of place, being, I think, the only physical scientist involved. So hopefully that it doesn't become too much. But anyways, the first thing I wanted to actually talk with you about today was talking about what we mean by a broken symmetry in terms of phase transitions. And with that, I'm actually going to talk about what we mean about new phases that exist actually near physical edges in materials. And when you think about phases and phase transitions, we usually think somewhere around here about ice, water, and water vapor. And I'll talk a little bit, I'll actually just show a picture here and there about superconductivity. And this is a pretzel, which hopefully you'll see why that makes an appearance in this talk at several points. The bulk of the talk will be spent talking about this, but actually in the latter half I want to focus on two things. I want to tell you a little bit about what I've spent a lot of time doing, what's really kind of led me basically back and forth across the Atlantic, and in terms of neutron scattering. And there's sort of two photographs here that I think kind of summarize things. And this is actually where the technique was developed in Canada. So Canada plays a bit of a prominent part in this talk, as you'll see. And this is actually the NRU reactor at Chalk River. It was built in the 50s, and it's going to shut down this March. It's really had kind of a great research career and things. So this is really the past in terms of this technique. And this is really where the field's going. This is the future. So this is a picture of the target at Rutherford Appleton Labs. The source is called the ISIS facility, and that I believe is based on a river, not anything involving political stuff like that. It's kind of an unfortunate name nowadays. But anyways, I'll explain a little bit about this technique. And then finally, at the very end, I just want to show you a very specific example involved in my research, where we've actually discovered some new properties that have resulted from actual physical boundaries. And I'll hopefully explain to you what I mean by an antiphase boundary. Okay, so this is where I kind of want to start the talk. So I want to actually talk a little bit about what I mean by phase transitions and what we actually refer to in solid-state physics as a broken symmetry. Now, when I mention the word phase transition, it's true, even the first thing that comes to my mind is basically this picture here, where you have this transition from a liquid like water to an ice. And what this characterizes is a situation where you go from something that's somewhat disordered to something that's very crystalline, nearly perfectly ordered. And we see this in liquid to solid transitions in water. What I'm going to focus on a lot today is actually taking a step back from this and looking at magnetic phase transitions. You'll see that actually you get a lot of the same properties here, but that occur in terms of magnets. You can get a lot of these types of phase transitions occurring, but instead of having atomic motions, now actually looking at small magnetic moments. And this is a picture here of a bar magnet where we've sprinkled iron filings around it. You can see that there's kind of a nice order around that. Okay, taking a step back and thinking maybe a little bit more abstractly in terms of what we mean with magnets. I want you to look at this picture up here. What I've drawn is kind of a schematic of a magnet, and what I've shown on this side is the material that's based upon small magnetic moments. So each one of these you can think of as a bar magnet with a north and south poles. But on this side here, actually you notice that on average, actually, the moment points in any direction. It has what we refer to as rotational symmetry. So overall, at this thing, it's a mess. There's no average net magnetic moment. The moments associated with these small arrows or these small bar magnets point in random directions. Now, what I've shown over here is actually see something very different. I've taken the same picture, except for now I've aligned all these arrows along a particular direction. And this is what we call a ferromagnet. So this makes up kind of something like your typical iron or your bar magnets that you have here. Now, this transition going from what we call a paramagnet to a ferromagnet is actually associated with a particular breaking of a symmetry. In this case, notice over here, you started out with, on average, a rotational symmetry, so the moments can point anywhere. And then over here, you've actually broken that symmetry. So now the magnetic moments can point along a vertical direction. Now, I think actually one of the nicest illustrations of all the different types of phase transitions based on broken symmetries you can get is actually kind of played out in liquid crystal phases. And I've kind of illustrated this down here. What I've shown here is actually a schematic of a liquid crystal, which is just basically well, okay, so my apologies to the chemists and biologists. It's just basically a goo of big, long molecules with a particularly long axis. And what I've shown you here is over here you notice you have just a mess, that all these molecules point in every random direction. And over here, I've shown you the opposite case. This is now something that's perfectly crystalline order. Everything's aligned along a particular direction. And if you look at the center of these molecules, you notice that there's pretty much perfect crystalline order. One of the nifty things about liquid crystals is actually between going from there all the way over to here, you can actually get some other interesting symmetries playing out. One is this case here. So this is called the nematic phase here. And notice what I've drawn here is actually a case where if you look at the center of the molecules, it's actually pretty disordered. It looks kind of like this. But notice that all of these things are pointing along a particular direction, in this case, the vertical axis. And so we like to call this thing having orientational order. And the particular symmetry that you're looking at here is actually the direction. It isn't the position of the molecules, it's actually the direction that they point in. Another kind of interesting phase transition that occurs with liquid crystals is what's called the symmetric phase, where if you look over here, you notice that they've kind of nicely aligned in rows here. So if you come along this vertical axis, there's kind of a nice density fluctuation. But within any one of these planes, it looks pretty disordered. This is called the symmetric phase here. Now, my apologies, but this is a physics talk, so I have to show some equations. But it's not so bad, so let me just walk you through this. This particular idea of breaking a symmetry. So if we come back to that picture where I've gone, where I have orientational order, and then I come over to here, and I plot here the symmetric phase, where you have this nice density oscillation as you go along the vertical axis. With all of these things, mathematically, you can associate what's called an order parameter with the symmetry breaking. In this case, so with the orientational order, we like to call this kind of a three-dimensional vector so it's something with direction and magnitude. Over here, the order parameter that we consider is actually the density as you go along the z-axis. So you can associate an amplitude with that density, and that characterizes the order of this phase. Now, if you plot the magnitude of this order parameter as a function of temperature, you always end up with a plot like this. So at high temperatures, when things are completely disordered, the order parameter is zeros. Now, at some magic temperature, could be the critical temperature, sometimes it's called the Néel temperature, if you're dealing with magnetism, that order parameter turns on and then grows down to the lowest temperature. And well, what I find actually really fascinating about this theory, this is actually called Landau's theory of phase transitions. I've called it universal because, first of all, so you can basically understand everything all the temperature dependence, all the properties of the system, just in terms of a very simple expansion based on symmetry. But what I find really interesting is that the same equation here that applies to liquid crystals, to water, to ice, actually applies to almost everything. It applies to, like, for example, piezoelectric. I'm always surprised when I go over to fluid dynamics that it's the exact same theory, the exact same types of expansions that apply for density fluctuations, and people think about in terms of chaos and stuff. So it's really, I think, very remarkable. This simple idea of symmetry breaking and an order parameter associated with that actually applies to almost everything. So this is actually a plot here I stole from an old journal published this article back in 1974. And they were trying to make this point here. So what they were plotting here is the order parameter for a magnet, a ferroelectric that's used in sensors. And, and this is actually associated with the soft mode frequency, with the structural transition. Now, one of the funny things you notice here is that all these new phases that we get, for example, this positional order and stuff, they're all associated with a particular broken symmetry. And these phases, just to sort of back up one slide, are really helpful for us. So this is an example here. These transitions here are actually exploited in things like liquid crystal displays, which you use in computer screens all the time. But now this kind of begs the question is, can we get new phases and new properties without actually breaking a particular symmetry in the system? Now, you might ask, okay, well, hold on, why should I care? This is all rather abstract. And there's kind of two applied examples which I want to talk about that kind of, I think, illustrate. I think the main goal of condensed matter physics, in particular materials physics, is that we're really trying to solve some very applied goals in the field of society. And one thing, actually, I thought was kind of brought out nicely. This is an article I found from 2000. It turns out he's from Toronto. It's not why I found the article, though. And so it's called Why Trap Light? And basically, this group here is being devoted with trying to design new materials to basically control how you propagate light through the material, which frequencies go through, the direction they go. They're known as photonic bandgap materials, PPGs. Sorry, I have to be careful. Now, so these are obviously of crucial importance to things like fiber optics, transmitting information. One thing that's beginning to come fashionable is actually not to use light to transport information, but actually to use spin waves or spin vibrations through materials. And the reason this actually becomes important is, unlike the case of electrical signals or even light, for some reason, when you actually transmit a signal with magnetic excitations, it actually doesn't actually lose any heat. Now, an interesting fact, you might say, okay, well, how's heat or whatever, how loss of heat in processing, why is that important? I thought it was an interesting fact. I heard it over the summer. So there's two things I heard. First, in terms of Google searches, one person told me that 2 Google searches can boil a cup of water. And then I quickly looked online and Google said, no, this is totally not right. It's 70. And I thought, okay, so if it's either 2 or 70 Google searches that boils a cup of water, it doesn't matter. Both are kind of bad news if you think about the number of searches we do, or everyone's doing as we get more computers and things. So we really need to actually find more efficient ways of transporting information, storing information, so that we actually don't, we reduce our carbon footprint, basically. And I think that's really what the big discovery was actually last year. So these are the 3 people that won the Physics Nobel Prize in 2016. And interestingly, so if you go to the webpage, it's for the theoretical discovery of topological phase transitions and topological phases of matter. You might say, okay, what does that mean? So basically, there are a couple of key things I took away from this prize. One, hopefully I'll show you, is that these are new phases of matter and new properties that come about from not breaking a symmetry like I'd be showing you. They don't come along with this nice order parameter that obeys Landau theory. There's kind of two aspects to this prize which I want to talk about. One is this idea of topology, the fact that you're now dealing with matter or properties on a surface, not in a bulk. And the second is this idea, which I'll talk about, is called phase in the material. So I'll get back to that. Now, with the idea of topology, I thought, okay, well, since I'm the only physical scientist, I have to point this out here. So this is something, there's a couple examples that come to mind on why topology, somehow when you put things on a surface and start thinking about how they behave, actually you don't always get what you might think is necessarily intuitive. One thing I thought is kind of neat is this idea, it's called the four-color theorem. This is totally a maths aspect, but it always strikes me as something that's wrong, but it turns out it's right. This was developed, first postulated in 1852, and the theorem says that if you take any map, so basically any array of objects on a 2D surface, you can color them with only 4 colors, in the sense that none of these countries share a boundary with the same color of one of its neighbors. So for example, if you look down here, you'll notice that this does not share a boundary with any yellow country, and likewise this country, green, likewise doesn't. Now, this plot here, I have to emphasize, when I was walking here, I thought maybe this is bad in terms of current geopolitical events. So but anyways, I think you get the point of this. But it always strikes me as kind of odd. Like when I first heard this theorem, I immediately thought I could come up with a counterexample, actually based on the map of Canada. But you know, it tends to always work. One of the funny things about this theorem was it actually took over 100 years to prove mathematically. And somewhere around the 1920s, people gave up and then downgraded to the 5-color theorem. But then eventually people realized, okay, actually 4 colors actually works. And I think it was only proved in the 1970s formally. Okay, that's something that's completely mathematical, but it's kind of, it's something I always like to play with. Every once in a while I try to actually go and see if I can develop a map or something based on more than 4 colors. But okay, anyways, the two other things I want to talk about in terms of how things behave in a strange way on the surface, and this comes back to more this being a physics talk, is this first idea here of moving an arrow around a closed loop on a surface. So now you have to really look at this and imagine what I'm doing here. So what I've plotted here is a sphere, and what I've done here is put an arrow at this point A. So this is literally an arrow pointing up. And what you do here is you move this arrow around, you go up to the North Pole. So keep in mind, remember the arrow's pointing up here. All right, you come back down to B. So now the arrow's pointing there. And when you come back to A, you'll notice that you're not pointing along the same direction, even though you moved along a closed surface. Now, it turns out this exact behavior here is kind of played out in this thing called the Foucault pendulum. Now, I was looking online. It turns out there used to be one in Edinburgh. I'm not sure if this is true. Yeah, and it's now in Glasgow, but I heard it's broken, which is kind of sad. But anyways, this is something if you get a chance to see, it's very interesting. But for 2 reasons. One of them you won't be allowed to see. I'll explain now. So the idea here is it's basically that this is an object so it's a ball attached to a long wire. This is actually a picture I stole from Chicago Museum's website. And if you wait around long enough, you'll see that if you're standing here, that this thing actually moves. And so that illustrates the fact that the Earth is rotating around you. Now, so that's the first interesting result. The second more interesting one, which unfortunately I don't think any museum will let you do, is if you wait for 1 full day and come back, or you stay there and look at it at the same time, you'll notice that the pendulum's is now pointing or oscillating along a different direction than it was exactly 1 day before. And that's not due to bad mechanics. That's actually a manifestation of this property I was just showing you here. And how far it's off actually depends on where you are on the Earth. Now, that was the first thing I kind of wanted to talk about. So that kind of shows you how things behave in a strange way when you put them on a surface. The second thing I want to talk about is this idea about phase. Now, when I talk about phase, I want you to think about a wave that's propagating. So what I've done here is just plotted a nice sine wave. And this is something I think everyone knows about. Like this, you can think about this as an electromagnetic wave, a wave going through the water. And you notice that this thing has basically two properties. One, the amplitude, so this value here, which I've nicely put to 1. And then also the period of this thing. So you notice it comes up, down, and then it comes back at a fixed point. Now, there's another important property that I haven't talked about, and it's illustrated down here. Notice I've plotted basically the same wave, except for I've shifted this thing in time. So if you take this point right here, you notice that it's at a minimum, but this wave is at a maximum, even though it has the exact same frequency and amplitude. Now, you might say, okay, well, that doesn't matter, right? Because all I care about is the frequency and the amplitude. But the funny thing is, if you add these two together, you get absolutely nothing down here. So phase does matter, and that it's going to be really important in the next few slides, actually. Just two other points that sort of quantum mechanical results, and they were actually shown by these two characters here. So this is Einstein. I'm sure most people recognize it. This is de Broglie. And so Einstein won his Nobel Prize for actually noting the fact that photons behave like particles. And this is something that's known as the photoelectric effect. So that was kind of counterintuitive. So we have this thing that's an electromagnetic wave, yet this guy's telling us that it actually behaves like a particle, and it's given by this energy here. And the factor h is actually so small that for all practical purposes, in normal days at normal temperatures, we can't see this effect. But it does matter for examples I'm going to show you. The second kind of Nobel Prize that talked about was the opposite effect. This was by de Broglie, and he showed that actually particles behave like waves. And he could relate the momentum, which is proportional to the velocity, to the wavelength associated with that. And lo and behold, it has the same sort of multiplicative factor, which is h, or it's sometimes called Planck's constant. Now, if you put all these properties together, actually it is very important. And to just illustrate that fact, I want you to think about this strange experiment here that I plotted. Now, again, you have to kind of think about what we're doing. So start up here, don't look over here yet. So what I've done here is actually put a magnetic field pointing vertically, and then I've induced this thing by actually running a current around this object. This is a lot like you might see in electronic components. So what I've done here is just really classical electrostatics, like putting a current around a closed loop, and that puts a magnetic field vertical. And this is governed by the right-hand world. A lot of this stuff was developed a long time ago. It's known as Maxwell's equations. But if you start throwing quantum mechanics and the idea of wave-particle duality that I was talking to you about, along with phase on top of this, you find out that, okay, if I'm going to think about this thing as a phase, the fact that it goes around a closed loop actually introduces this extra phase factor to it. So what I've done here is actually written some very formal quantum mechanics. So I've written what's called the wave function of this electron. But you'll notice it's broken up into this thing, which is essentially an amplitude. But then there's this thing out here, which is actually the phase of it. And this thing does really exist. This was nicely shown in this. I stole this right from PhysRev letters, so sorry about the contrast. But what I want you to note here is that if you go along the vertical axis, this oscillates from being black, white. This is called an interference pattern, and that's exactly the type of thing I was showing you before. This is the case when you have two waves interfering. They'll give you this picture. So this is the hallmark of something behaving like a wave, and it appears all the time in quantum mechanics. It's a real effect, actually. Okay, so if we come back to the fact that we have this simple experiment here where I'm passing a current around and I got a magnetic field and I have the electrons here have a phase and an amplitude. Okay, now so what? Now, you have to kind of go up to about 1980 with something called the quantum Hall effect. And it turns out that this manifestation of topology, the fact that you're going around a closed loop, and you have this phase, means that actually the current you can run around this thing is actually quantized. And what I mean by that is that it can only occur in certain discrete values. So what I've written here, again, is the current that you can move around this closed loop. And you notice that there's this factor here of E squared V over H bar. It's just a number. But what's important is this factor of M here. And M can only be an integer. It can only be something like 1, 2, or 3. And this tells you that this current here has to be actually quantized. Now, just to show you that this is a real effect, and this actually resulted in another Nobel Prize, is that in this paper here, what they did was they actually showed this. So they actually plotted out the current. You can see these little steps here. And this thing that shows spikes is actually the first derivative. It's just showing you the gradient here, but it's just illustrating that there is quantized steps. And based on these steps, they could actually directly measure this thing here. Now, I know this doesn't mean a lot to people. This is called the Finestructure constant, and it's a fundamental constant in actually all physics. It goes as E squared over H bar C. Now, I always get myself in trouble with this part of the talk because I like to say, okay, in condensed matter physics, we can directly measure this, end of story. Now, if you're in particle physics, you have to go to some supercomputer and calculate, I don't know how many Feynman diagrams, and then you come up with basically the same answer. So I always like to break. In condensed matter physics, we're actually ahead of the game on this. But as always gets pointed out to me, so this is kind of a full disclosure, that the error bar you get in condensed matter physics is actually significantly more than what you get if you actually go use your supercomputer and calculate all those diagrams. But I think it's still very interesting that you can actually directly measure this. And this is a direct manifestation of these ideas I was talking about in terms of particle duality and also phase. One funny thing that came about in actually all of these experiments was that this effect here seemed to be remarkably robust to disorder. In fact, the data seemed to get worse the purer the samples are. So that was always a bit of a mystery. And it was really actually Halpern in the early 80s that really suggested a way out of this. And he pointed out that if you take a particular material and you actually do this experiment, so you apply a magnetic field, and classical electrostatics forces the current to go around a particular direction. The fact that you have this phase and particle duality giving you this quantization means that actually the current likes to do this. It likes to jump around on the edges and go around like I've shown you here. And because of all these things, this edge current is actually really robust to impurities. In fact, it seems to be somewhat better. So if you have lots of impurities in the bulk, it doesn't matter. The current around the surface has to do this because of these laws of quantum mechanics. And I always find this rather cute. And this is actually coined by two theorists at Stanford University. They like to call this traffic control because if you point the field vertical, you can force the charge around a particular direction. If you reverse it, you get the opposite field direction. And of course, you can stop it. So they always like to talk about it like this. But this is kind of a nifty example of where edges are actually really important. And this is actually where I think the pretzel first makes an appearance. I was always mystified when they announced the Nobel Prize. They always brought a pretzel with them. But the pretzel is kind of a nice example, you know, because it always has to have 3 holes or 3 quantized parts to it. And that's actually key to the idea of some of these effects. The other important thing with this Nobel Prize in terms of surface was this idea of a topological insulator. Now that sounds like a bit of a mouthful, but it's actually a really simple idea that I try to illustrate right here. What these theorists did, and they actually experimentally found this, was if you think about a metal and you plot out the band structure, what you get is something basically that looks like this. So you have your electrons at a certain level, and you can basically, they can flow. So there's no energy cost to move them around. Now, what I've done here actually is I've moved those filled levels, and I've actually put them at a higher energy than the unfilled levels. Now, this is really unusual, and you might say that this is unstable, but in materials, you can actually engineer this type of structure. So where you have your electronic levels filled with your electrons actually living higher up than the valence of the whole, than sort of the empty levels. Now, if you take this and put it on a surface, think about what you've got. If you go to air, it's just simply this, where you have, all the electrons are filled up to a certain level, it's an insulator, and you need a huge energy scale to excite them. But now, look at these two pictures here, the way I've drawn it. So here you have this filled level up here, and on the surface, you then have to go to this type of structure over here. Now remember, despite what physicists like to say, the world has to obey continuity. So we have to be able to continuously move from here to here and here to there. So the only way to do that is if I collapse this thing down and then raise it. And what that does is it actually introduces states at the surface that can flow with basically without any energy. And this is actually a result of topology. This is the fact that you have to be able to continuously deform this structure to this one. So you have to do something really fundamental. You have to break down the structure basically and then restart and reverse it. And that actually gives you these electronic states on the surface that can flow without any energy cost. I always like to think of it a lot like this picture here. This is exactly the same story. This is, again, where I think the pretzel is kind of a nifty example. It's the case that if you want to go from a pretzel to a croissant, you notice you can't continuously deform the pretzel. I don't think you could continuously deform the croissant, but I'm not going to think about that too much. But if you want to actually go from here to here, you have to break down the substance. You basically have to break it down to its constituents and start again. That's exactly what the picture's being done here. Okay, that's a rather abstract example. One actual real-life example that I think people are familiar with. It turns out this kind of thing has been playing out in the field for some time, not in the context of these topological insulators, but actually here. This is called polyacetylene, and it's kind of a very simple molecule, I think. It consists of 2 carbon double bonds here. So my apologies to the chemists in the crowd, and a single hydrogen. And the nifty thing that was actually discovered by these 3 characters and was the subject of a Nobel Prize was actually the versatility of this thing. The fact that it could be an insulator, i.e. not a very good conductor, it can't conduct electricity. But by changing the chemical properties, you could actually turn into a very good metal, something like copper. And it was really, I think, the physicists that pointed out a nice way to do this. So this is actually, I think, was headed by these 4 characters here. But think about this. So notice what I've done here is I've plotted that molecule. So here's a single bond, there's a double, single, double, so on and so forth. And then we pick it up over here. We have a double bond, single, so on and so forth. Now, look carefully at the picture here and compare it to over here. You'll notice that the double bond has swapped positions. So what you've done is you've actually introduced what we call an antiphase boundary. You've basically, we like to say, shifted the whole structure over here by pi. And this thing sometimes is called a soliton. It turns out, so if you think about the electronic structure over here, and that being compared to that over there, and thinking about these same topological arguments I was talking about to continuously deform from that structure to that, you actually need to have metallic states that live at E = 0. So this is really, the fact that you can make these things conductive is really actually comes about from topological arguments. The fact that you can shove in this antiphase boundary, or what people like to call solitons. Now, of course, everyone's going to understand this slide perfectly. So anyways, but now these topological ideas, actually what I'm trying to point out in this slide, even though it's a bit of a mouthful, unless people are experts at partial differential equations, I'm not particularly keen on them myself. But anyways, these topological ideas actually play out in magnetism at the atomic level. And one of the things that actually comes about from the theory I've been talking about, the fact you have this quantization and this phase, is that you can basically have 2 types of magnets. One where the magnet is kind of an integer, so you can have integer values of a magnetic moment, or you can have half integers. And it turns out both of these cases have very different ground states. It turns out this one here actually is degenerate, where the spin 1 actually isn't. It actually has a very different excitation spectrum. There's many ways you can create these. I just put this up. This is actually largely a Canadian collaboration where you can actually pair up spin 1/2 magnetic moments to create net integer spins. But anyways, that kind of leads me to this idea that I want to sort of take a break and talk about neutron scattering, because the fact that these topological ideas I've been kind of illustrating early on actually can be directly measured with neutrons. And neutron scattering was actually the subject of a Nobel Prize in 1994. Now, being Canadian, now if there's any Americans in the crowd, I'm going to apologize. You can come get me afterwards. But anyways, we like to think of this really as our Nobel Prize in Canada. There's very few examples, particularly in Canada, where the science and all the engineering, all the technology was actually developed. And it was really kind of spearheaded by this character here. This is Bertram Brockhaus. And the place this really happened was at Chalk River Labs. And what they got the Nobel Prize for was actually looking at excitations in matter with neutrons and also the structure of materials. Now, you're probably wondering right now, well, neutrons, this sounds like rather a complicated way of looking at the structure and properties of materials. You know, I got X-rays. That seems to work great. So what is so special about neutrons that really make them an ideal probe of materials? And to illustrate that, actually, I want to throw up some numbers here. Now, so what I've done here is actually written out some values. So I've taken a wavelength of 1 angstrom. And the reason I've picked 1 angstrom is because that's usually something on the order of typical atomic spacing in materials. Like, okay, usually it's about 4 or 5, but okay, it's about 1 angstrom. And if you take 1 angstrom and you think about the energy scale of an X-ray that you need to actually have that wavelength, it turns out you need this. You need 12.4, and that K is kilovolts. That becomes important. And the reason why this is actually such a huge number is this. If you think about the average energy scale of materials, you're thinking something on the order of room temperature, about 25 degrees Celsius on a really, really warm day, or usually about 10, right? And so in that case, you're usually thinking about energy scales about 25, and that's millivolts. So you're many orders of magnitude down, or actually up, with X-rays over what you're actually measuring. Now that becomes really important, because if you think about the analogy I always like to draw is if you want to look at a crater on the moon, you don't go for a microscope or even a meter ruler. What you go is for a telescope, something that really is matched for that length scale that you're interested in studying. So it's the exact same thing if you're looking at energy scales, temperature, whatever. So this is really a massive energy scale, and that comes about with X-rays. Now, with neutrons, it turns out, okay, neutrons, there's a few key differences, which I'll talk about. The first is that they're massive. They have a magnetic moment. And they actually interact with material slightly differently. But the key thing is that notice for that 1 angstrom length scale, again, you now have a much lower energy. You've got something that's much more compatible with the energy scales you're after. These are just sort of 2 cartoons that I took. This is actually an accelerator in New York called the National Light Source that this actually produces X-rays. This is a schematic of a nuclear reactor outside Washington, D.C. that actually produces neutrons to study materials. I'll show some more pictures in a second. Another key thing that's rather nice with neutrons over X-rays is how the neutron cross-section varies as you go throughout the periodic table. Now, if you think about what X-rays are sensitive to, they really interact with material with the electrons. So they're going to scale basically as the atomic number. So you go down, and at the bottom of the periodic table, you got a ton of electrons. It's going to be a big X-ray cross-section. So that's why I think in medical facilities, they usually like lead, for example, because it's down here somewhere. It's a really good absorber of it. And this is an illustration here. So this shows the cross-section of X-rays in terms of spheres as basically as you're moving down the periodic table. You can see it nicely monotomically grows. The problem is, though, is that, for example, if you're interested in a material like this that has lead and oxygen, it turns out with X-rays, you're just going to see the lead. Now, neutrons, on the other hand, actually the cross-section varies, because it interacts via nuclear forces, it actually varies fairly erratically throughout the periodic table. Now, there's a funny story about this slide. I once got into a lot of trouble because I said that, I mentioned this point that, okay, I don't understand nuclear physics. The cross-section varies erratically. Can we move on? It turns out there were 15 people in the audience that were nuclear physicists. They did understand this, and they were not happy. So anyways, my apologies to any nuclear physicists in the audience. But anyways, just a further illustration of that, what kind of the nice contrast you get with neutrons is if you take these two characters here, carbon and nitrogen, notice that with X-rays, because they have similar atomic numbers, 8, they have similar X-ray cross-sections, but with neutrons, it's almost a factor of 2 difference. Now, that interaction via nuclear forces also means that you can actually probe materials. It actually is a very bulk probe. When I mean bulk, I mean centimeters. It can really go through, neutrons can easily go through about 10 centimeters of material. And that's used in industry. So this is actually a plot here of the Engine X instrument at the Rutherford Appleton Labs. Now, this takes a bit of imagination, but out here you have your incoming beam. And so, unfortunately, this person's standing in front of the beam stops. So when actually it's happening, the beam's off. But anyways, and this array here is actually the detector. And what they have here is an aircraft engine. This turns out this technique is used a lot in the aerospace industry. Because neutrons penetrate at such long length scales, you actually don't need to break down your aircraft engine wing or its various components. You can just take the raw component to the neutron beam line, if it can fit there, and basically scan throughout it. And one of the things you're always interested in is basically the atomic spacing. And neutrons, again, by the wave properties, actually follow what's called Bragg's law. So for particular wavelengths, at particular scattering angles, you're actually sensitive to the displacements of the atoms. These are just some pictures of some instruments at reactor sources. This is a picture at the ILL, and what you have here is this is where your sample lives. This is the detector array. This is SPINS at NIST just outside Washington, D.C., and this here is the MAX instrument, which is basically this, but it consists of an array of detectors. Now, this is kind of based on older technology, and that's what I want to illustrate here. One of the problems with neutrons that you can kind of see is that you need a lot of material to study with neutrons because they interact so weakly, and that's a problem. So you're always flux limited. So this is a plot here of flux at various neutron sources, reactors, and accelerators as a function of years. So we have 1940 out here. This is sort of the first experiments in Chicago. Up here we have Chalk River. You notice that reactors basically hit their limit fairly quickly. And it turns out that's an engineering limit due to how much heat you can get out per unit time. And what's really exciting at the moment with neutron scattering is this curve right here that's really taking off. Actually, I would argue that it's actually a little bit more concave up. And these are accelerator-based sources. And a lot of this has been driven by this facility down at Rutherford Appleton Labs. And the UK has really played a major role in this. So this is actually a picture here of the whole Rutherford Labs setup at the moment. This is the main accelerator ring. And it's based on 2 different target stations, which are based on tungsten. So the way you get neutrons in this case is having a proton beam hit a tungsten target. And that proton beam is pulsed. So your whole experiments at your detector and sample are all based on timing. So you time when the neutron leaves the source, when it hits the sample, and then when you detect it. So this is really a new way of actually doing the experiments. And it's actually really exciting developments because really you can see that from that plot that in terms of flux now, we're no longer limited by these sort of heat problems at reactors. So this is being exploited at Rutherford Labs, and there's also new sources being developed actually at the ESS in Sweden at the moment. Now, I want to show you two examples of kind of nifty things that neutrons also tell you about material. That I've already pointed out they're very sensitive to the structure of a material. And just to illustrate that, I'm plotting here two pictures, both neutron cross-sections. One is a very perfect crystalline ferroelectric material. It's based on this. And this is the same material, except for where I've kind of messed up one of the sites here. I've introduced some disorder into it. And what's so neat about this picture, I think, is the fact that it's qualitatively very different. You can see immediately the effects of disorder in the cross-section with neutrons. So this is actually one of the really nifty things that you get with neutron scattering, the fact that it's so sensitive to structural order. The other thing you get, it's a bit more involved, and it requires a little bit work experimentally, but you basically get what I'm trying to show up here, and that's the strength of coupling between atoms and materials. And one of the nice things with neutrons is that it's equally sensitive to the atomic structure, the nuclear cross-section, as well as the magnetic structure. So here I can get both the kind of strength of how strongly two atoms are coupled, or I could actually put small magnetic moments here and see how strongly they're coupled, just from sort of doing dispersion curves like this. So these are actually pictures from data taken at the Rutherford Appleton source. I won't go into detail too much, but I always kind of find it nice just to show some real data in this whole thing. Okay, that's all I wanted to say about neutron scattering, just sort of in the last 5 minutes or so. I wanted to actually come back to this idea of topology and what neutrons has really done for this. Now, you notice about 10 minutes ago, I pointed out that in magnets, you can have half-integer spin type systems or integer spin. So spin a half and spin one. And I said, okay, they both have very different ground states and excitation properties. And you can directly measure that with neutrons. This is an example here of actually a half-integer spin. And I'm not going to actually explain this, but I want you just to remember what this looks like. Two key things is that you notice that there's intensity regions right down close to E equals to 0, and there's kind of a broad spectrum of stuff as a function of whatever this axis is, Q, and also energy. But just qualitatively, remember what you have there. Now, the interesting thing is this is the spin 1 case. Now, this isn't a nice color plot because you can't get it, because instead of having that nice smeared data, you just get a very sharp single, what we call delta function peak. And so you get curves that look like this. So first thing you get kind of something that looks boring. You have this nice sharp spectrum. But the other neat thing that you get with the spin 1 case is you get this little gap here that appears. And that was predicted in the context of topology by Haldane. So it's known as the Haldane gap. And this was first shown actually at Chalk River and published back in 1986. Okay, just in the last couple of minutes or so, I wanted to actually point out a nice example of where boundaries in topology actually plays into my own research. We were studying this, honestly, sometime before this paper came out. This is a paper in a mineralogical journal. I thought this was rather cute. This is published in 2014 on this new mineral they found, calcium ferrite, and the physicists, we've been studying this for quite some time. And I thought this was kind of nifty, the fact that it's now made this resurgence in the mineralogical world. And it was discovered actually near the West Bank in mineral form. Now, the structure of this thing looks like this. Now, okay, I know this looks a bit weird, but let me just explain what I plotted here. As I plotted the magnetic moments in this material in real space. And you notice what I've done here is that it consists of these kind of double chain frameworks here that kind of alternate in how they're angled as you go down this axis right here. And what I've done is I've actually denoted the direction of the magnetic moment on these individual sites. So you can think about this little north-south magnet attached to each one of these different sites. And the direction of that is actually indicated by the color. So red means the magnetic moment's pointing along one axis. Blue means it's reversed. So basically, you've swapped the north and south poles on the blue and the red. Now, instead of plotting this, actually, I like to plot the structure like this, just because it's a lot simpler to think about. But you'll notice that, on average, there's the same number of blue as you do red. So this thing does not have a net magnetic moment. If you apply a magnetic field to it, it's just going to do nothing, because the different directions, on average, all cancel out. The neat thing about this material is that you have two competing magnetic phases, and you have this other phase over here. One's called A, and the other one's called B. And you notice here, globally, this thing doesn't have a net magnetic moment. There's the same number of red spins as there are blue. But in this case, instead of having blue, blue, red, red, what you have is a structure that's red, blue, red, blue. So it's just in terms of how you stack these different colors. Okay, I plot the same thing here. Here's the two phases again. We got the red, blue, so on and so forth. Down here we have the other magnetic phase. And notice what I've done down here. So I've taken this structure, I've gone blue, blue, red, red, blue, blue, red, and then I've introduced a wall here. This is known as an antiphase boundary. And look at this side here. Now think about what this thing looks like without this boundary. You would have red, blue, red, blue. But because of this boundary, this side over here is actually out of phase with the structure over here, just by the single direction. It's very analogous to what I was showing you with polyacetylene. It turns out now, again, this thing is locally disordered here. So this is an antiphase boundary. It's something that shouldn't be there. And this is something that appears obvious in neutron scattering. This is something we can easily measure, just like those two nice pictures I was showing you before. I won't have time don't really want to talk about this, but it's an interesting aspect of neutron scattering if everyone wants to come up and talk about it. These boundaries actually turn out to change fundamentally the energetics in this system. So you notice in those curves I was showing you before with the spin-1/2 and spin-1 magnets, you always had these nice continuous lines. And because of these boundaries in this material, you actually don't get that. You get a spectrum that's actually broken up into discrete bits, and there's not a nice continuous curve like I was just showing you. And this is very analogous to like those photonic bandgap materials I mentioned at the beginning of the talk. There's certain energy ranges where this thing just will not propagate any excitations through. Okay, so that's actually where I wanted to leave this talk. So first of all, you might notice, just to summarize, I talked a little bit about topology and new phases in materials. I introduced this idea of a broken symmetry and why, when you're near an edge, sometimes you can get new properties and new phases that don't involve a broken symmetry. And this is kind of a nice schematic of that topological insulator I was talking about. Hopefully I sold you a bit on neutron scattering in the middle of the talk, and then I finally talked about boundaries in nice small magnets that are involved with my research, and hopefully you remember why the pretzel is important. Now, there's a few people I want to thank before I go away. I'm really lucky to actually be working with a lot of exceptional people in this field. Particularly, a lot of this research was supported from Rutgers in the United States, the University of Maryland, and also at the NIST facility. And in Europe, we've been working with actually a lot of people at different facilities in France, in Switzerland, and in Germany, as well as in the UK here. And of course, all of this wouldn't have been possible without funding that we've received from a couple organizations. Particularly recently, EPSRC's been very supportive of our work. And we're really indebted actually to the Carnegie Trust, because they really kick things off in terms of our research, and also the Royal Society and the STFC. And finally, one more slide. I want to thank the people who put this nice kind of collection of talks together, particularly Jamie, Sarah, and Matthew, who I've been interacting with for the last little while about this. So anyways, and thank you for attending and listening to this.
Some of your talk was stressing surfaces and some of the interesting properties at surfaces.
That's right.
And then when you talked about neutron scatter, one of your one of the properties that was favourable of neutrons is that they go deep because they don't interact that much.
That's right, yeah.
Doesn't that mean you're therefore missing some of the most, on average, you're missing some of the most interesting things, whereas hurling some horrible charged particle would get you the surface straight away?
Like you're looking at the surface. That's true, except one of the nice things with neutrons is they're actually, particularly these days, easy to manipulate. So you can take your material and actually do what's called reflectometry, where you actually are only looking at a very close surface. Now, one of the things you get with neutrons that you don't with like X-rays, for example, is this magnetic moment that appears with neutrons. So X-rays, you have to, I don't know, go out to how many orders in perturbation theory to actually get the magnetic cross-section. With neutrons, it's there and it's just as big as the nuclear cross-section. So it turns out it's a little bit easier, and the fact that we can manipulate neutrons so easily means that we can actually do that experiment you're talking about fairly easily. Yeah.
Thanks for a very interesting talk. This is possibly a naive question because my chemistry days are long behind me.
I'm in trouble.
With the polyacetylene, I noticed that with the change in phase, you were showing kind of dots where the single and double bonds would have been.
Yeah.
And that just reminded me of kind of benzene and other aromatic compounds. So I'm involved in drug development, pharmaceuticals. So I'm wondering whether these kind of symmetry, like the symmetry changes and the direction changes, whether that could be important in drug development.
Yeah, I think that's absolutely true. And I think there's lots of examples of this case where people looked at the atomic structure that I'd be able to introduce boundaries, like I was illustrating. I'm not sure if it was being done with benzene, but I know that's a really spot-on question.
I'd like to thank you again very much for a most interesting talk. Thank you.